All right, let's do this thing. So, what we have here is a diagram of the electromagnetic spectrum. A little bit different from what I've been showing you guys. We got the lower end of the spectrum, or low energy, over there on the right, and then the higher end of the spectrum over here on the left. But it's all the same thing. You got low frequency, high wavelengths on the right here, red light, and then violet light right there. So basically, if you took a prism of some sort or something, and basically were able to expand any sort of visible light on an electromagnetic spectrum, you would see this spectrum show up on any sort of diffraction grading or something like that. You would see the spectrum show up, and this would be for like any sort of like sunbeam you sent out or anything like that would show this, which is visible light. So any kind of white light would show up. This is what we call a continuous spectrum. You go from red to violet, and we see just every color in the rainbow all the way there and there. Just to give you guys a quick sort of example of what that looks like, I got this video. Yes, I know, video within a video, but it does a... Let's cut this sound out.
Hydrogen.
Shut up.
And this is what it looks like.
There we go. So this is a hydrogen beam right here, and then it's put through a diffraction grading, so you can kind of see the spectrum or the colors that it puts out. We call this an emission spectrum. This is the colors that it's emitting. And you can see the little bands of different colors that are showing up right there. Once again, I'm colorblind, so it's kind of hard for me to see the difference, because, well, yeah, but you can kind of see the pattern it shows. This is, I believe, helium. So helium shows kind of a different spectrum. It shows a different kind of color. But again, you notice if we show, and let me say here, what's happening here is that there's a current going through this wire here. There's a current going through this gas, and it's exciting the gas, and that gas is letting out what we call an emission spectrum. I'll talk more about that in a bit. So what you saw in the past here was a hydrogen emission spectrum, and then what you're seeing here now is a helium emission spectrum. So the spectrum are the colors that are given off when you excite helium gas. This is the colors that are given off when you excite a hydrogen gas. So let's see the rest of these, because I think what shows up next is nitrogen. And I could be wrong. I could be getting these all messed up. But at least you get the idea. So I think this is nitrogen. It's a little more complex. That might make more sense. Maybe the sound I would want to put back on to see what this person's putting up there, but you can see all the little lines and everything like that. That's the spectra that it puts out there, and we'll see this again when we talk about a little bit of let's not do Mr. Anderson. All right, you're going away. Yep, thank you, well done. Okay, so yeah, basically what we talk about with an absorption or an emission spectrum, like we were talking about, is what was happening is we were emitting, we were exciting hot gas. We were placing that light that's emitted from the hot gas through what we call a diffraction grading. So a diffraction grading, that's what this is right here, and it can split up that light into the varying colors that it's made out of. Because again, if you take all the colors of the spectrum and put them together, you get white light. And this is what comes out. So if you got something like, I think this is hydrogen. So this would be hydrogen here. This is the emission spectrum. And you can probably guess an absorption spectrum does the absolute opposite of what an emission spectrum does. So if I just have a really high density hot light, so just a hot light that emits essentially the colors of the spectrum, and I put some sort of gas in between that, well, this gas is going to absorb some of this light, and what's left over is going to be what we call the absorption spectrum. And this is what's left over of that absorption. As you can see, though, these things are giving us different patterns. These kind of different interesting patterns. hydrogen was different from helium, which was different from nitrogen, from what we just saw right there. And physicists were noticing this about elements, that we could basically, it's often called the thumbprint of the element. We're able to determine which element is creating this emission or absorption spectrum based off of just the pattern that they create here when put through a diffraction grading, which is kind of nice. And we'll talk more about how that's useful when we get to astrophysics later. People were to predict what kind of wavelength these kinds of emission spectrums were able to create. This is all the hydrogen line of the spectrum. So these are all predictions that were made from hydrogen. So what people figured out here, and we got different people here: Lyman, Balmer, Paschen, Brackett, Fund. They all started getting their own. We'll start with Lyman. Lyman was basically like, "Hey, yo, when I do the inverse 1 over the wavelength of the light that's being projected here, it's equal to this constant, this weird constant that we call the Rydberg constant, I believe, something like that. It's equal to that constant multiplied by 1 divided by the 1 squared minus 1 over n squared. I think Balmer was the first one to do this. That's why it's kind of in this form, but we'll talk more about that later. And then minus 1 divided by n squared. And n in all these things, n could equal 1, 2, 3, 4, blah, 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 kind of thing. Although here it can only be 3. Here it starts at 4. Here it starts at 5. Here it starts at 6, etc., etc., etc. Okay, so yeah, and so basically, then you got Lyman, Balmer, Paschen, Brackett, Fund. All these people all come up with what looks like some sort of, you got to be able to generalize this some way, right? Oh, gee, I wonder what the pattern is that's happening here with these things. However, this Rydberg constant, let's see, ended up being 1.097 times 10 to the 7th, and then inverse meters right there, 1 over meters. Was this constant, and we'll talk more about this in just a moment. So as you can see, we're kind of getting this general formula here that it's 1 over the wavelength of the light that's being emitted, or the photon that's being emitted here, multiplied by the constant, then multiplied by 1 divided by nf squared minus 1 over n initial squared. We'll get back to this in just a moment. And again, any of these n's are equal to 1, 2, 3, 4, blah, 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 blah. However, in such a way, you got to plug these in such a way you're only going to get a positive value out of this. I can't do like 4 minus 2 or something like that. That's not going to work out and give me a negative number. Okay, in comes this Neil Bohr guy, right? And Bohr says, wow, cool. And he uses well, first he's a student of Rutherford, which, hey, that might look familiar. That looks like the guy who I found out shot the gold or shot the alpha particles at the gold plate, and figured out that the atom had a dense positively charged nucleus, right? And then there was these electrons that were zipping around around there. And Rutherford used basically what we kind of consider like a solar system model, that in the center is a positively charged nucleus, and then electrons zip about them. However, even Rutherford kind of figured this out. He said, oh crap, I got these electrons that are zipping around here, and if I got a charge and that charge is moving in a circle, well, circles are unnatural, right? Circles aren't natural. So in order to have that happen, this happens because the electron is attracted by the electric force to the positive charge there. And that means then that if this electron's moving in a circle, it's got to be accelerating. And if a charge is accelerating, as we found out with those Doshgarn electromagnetic waves, is that, oh, if the charge is accelerating, it emits a photon. It emits light. It radiates energy. And he found out that that energy would dissipate in actually less than a second and just crash into the proton. So his model, while working for all the experiments that he had, did not work in the calculations he was making. He was doing the calculations like, holy crap, this can't work at all. This can't be true. So Bohr picks up where Rutherford leaves off, and he says, okay, all right. So Rutherford's model is making sense. This is right. And he does something similar to what Einstein does with relativity, is he says, I'm believing Rutherford here. There's a dense nuclear, positive nucleus in this atom, and there are electrons dancing around it. Now, how does this work? You know, I got to make it so that this thing stops radiating, because that thing's just going to crash right into the nucleus. That doesn't make any sense. So he basically starts off with, okay, matter's stable. I mean, okay, we look around and we see matter's stable. Everything's not collapsing in on itself, so that's got to be a case. He also says, atoms emit and absorb discrete spectrum. Here we go. Here's where things getting kind of interesting. Basically, he says that let's see. He also says that emission spectra can be produced by collisions. And what he means by this is that if I got a photon, so here's let's keep going here. Absorption wavelengths are subset of the wavelengths in the emission spectrum. Okay, let me break this down in a little bit more English here. What he's basically saying is that, all right, electrons orbit here's a proton, here's a nucleus. Electrons orbit that nucleus, but they can only orbit these spots that I say so. Those are the only spots that they can orbit. They can't go in between. Like, you can probably think of an orbit in between Mars and Earth. You can probably think of an orbit between Earth and Venus. You can probably think of an orbit between Jupiter and Mercury, right? You can think of orbits in between those. Those are fine. There's nothing wrong with them because those orbits happen in a continuous amount. Where these, Bohr is saying, no, here are the only spots those electrons can orbit. Everything else is off limits. Nothing else is allowed. And he's trying to justify, give a reason as to why that essentially electrons don't radiate away their energy when they're orbiting these protons. Okay, so he's so what he's basically saying is that, okay, but light could show up. Here's a photon of light, can show up, hit that electron, and then jump it to a new energy level. That electron can then gain the energy of that photon. It absorbs the photon and then can jump to another energy level. And these are the energy levels. Energy level 1, 2, 3, 4. So if the electron gains the photon, it gains energy and can jump to another energy level. Other than that, it goes down to its lowest energy level. And the lowest energy level a photon can reach is where n equals 1. We'll talk more about that in a bit. And so that's basically what Bohr is saying. And he's also saying is that, okay, if an electron jumps up to a high energy level and goes down to a low energy level, it'll actually emit a photon, kind of thing. So that's where Bohr is coming from. And he even is, so here are his assumptions right off the bat, which are already flawed. And even he knew they were flawed, because he even went a little further and said, okay, I'm also going to say the angular momentum of all of these photons, and he said the angular momentum has to be quantized. He said the angular momentum has to be quantized, and that angular momentum is equal to n. This is the quantization, because n could equal 1, 2, 3, blah, blah, blah. So that angular momentum L of any electron orbiting around this thing is equal to Planck's constant h, which remember h equals 6.626 times 10 to the negative 34 joules seconds, h over 2 pi. And I'm actually going to, because this shows up a lot in quantum mechanics, and instead of saying h over 2 pi, we call it h bar, because it shows up so often. We end up just saying h bar. So, but please remember that it's h over 2 pi. So, okay, I got the angular momentum is equal to some quantized number n times h bar right there. So that's his first kind of thought. Then he goes, all right, okay. So I got this electron. The electron's going to be my system, my object here. What are the forces acting on my object? We're going back to classical physics here, folks. Okay, what are the forces acting? Well, I got an electric force. The electric force is acting on my object, and that's it. That's what's causing the centripetal acceleration right there. So using F net equals ma. Well, that's going to be the electric force is equal to m, and then it's moving in a circle. I'll give you that hint. It's v squared over r. So it's v squared over, I'm going to use baby r here. All right, so there we go. Okay. So I got that. I'll give you one more little hint. The Coulomb force that we found out. The Coulomb force that we found out is equal to Ke, the Coulomb constant. I'm going to use K instead of 1 over 4 pi epsilon naught, just to make things a little more easy for us. So that's a constant you can look up. Q1, Q2 over r squared, over how far away it is squared. And as for the charges, I'm going to say, well, the charge of an electron is the elementary charge E, and the charge of a proton is also the elementary charge E. That is, the magnitude is E. So you can think about what to plug in for those charges there, right? Because Q1, Q2, right there. So you can get those. Okay, and I think it's just from those. You should be able to derive the expression so just from these three, I think it's just from these three, you should be able to derive the expression R. We do R sub n. So any of these R's, when you start to quantize them, so if the if on the other side of the equation involves like this n value here, we use R sub n. So this will turn into R sub n, or this would turn into R sub n. R sub n equals h bar squared over the mass of the electron times the Coulomb constant multiplied by the charge, the elementary charge squared. So that's what you got to do. Use those equations to derive that expression right there. Once you got that expression, I want you to also then use the fact that, let's see, I'm going to zoom out just a little bit here, because I also want to use the fact that the energy of any system is equal to the kinetic energy plus the potential energy. We're going to assume non-relativistic. So in other words, I could plug in the kinetic energy equals 1/2 mv squared here. That's what I mean by non-relativistic for that. Nope. I just realized you need one more equation here for this first part, so I'll throw it in there. Is that, assuming non-relativistic as well, is that angular momentum is still equal to the momentum multiplied by r, right? mvr. So that's also something you're going to use. You can still, so this is non-relativistic, so you can still assume the angular momentum is equal to mvr. And here even kind of shows up at the beginning of our discrepancies between relativity and quantum mechanics already, is that we're throwing away relativity and deriving this stuff. Okay, sorry, going back here now, non-relativistic, so the energy equals the kinetic energy plus the potential energy, which the potential energy obviously is going to be the electric potential energy. I will also give, so there's that. So we're going to use this at some point because we're going to find the energy of this electron orbiting the proton. We're modeling the hydrogen atom here. We're modeling the hydrogen atom, and in a hydrogen atom, you get one proton and one electron. So that's all we're going to focus on right now. Okay, and in doing that as well, you're going to get the electric potential energy. Well, the electric potential energy is the Coulomb constant multiplied by Q1, Q2 over R. And that's negative right there, right? So hopefully remember deriving that electric potential energy function. Wow, that looks a lot like the gravitational potential energy function right there, which was negative big G M1 M2 over R, yada yada yada, right? So yeah, and we got a positive charge and a negative charge. The potential energy is negative, and then the magnitude of those charges there. You know what? I'll even go a little bit further. This is going to be the potential energy is negative Ke E squared over R, not R squared, just R. Yeah, so there's my potential energy there. Basically, I want you to use these two ideas. Again, use those two that I just highlighted right there for you to get to this energy. So again, if n is on the other side, we usually use E sub n. So that just means the total energy. That the total energy is equal to negative mass of an electron multiplied by Coulomb's constant multiplied by the elementary charge to the fourth power, divided by 2 h bar squared. And then also multiply by 1 over n squared. And there you go. So get to this. And then one last thing I want you to do is plug in all the values for this. Plug in all the values for this. You're going to get, well, n is a unitless quantity, so you're going to get something in terms of joules. And what I want you to do is convert that to electron volts. So convert joules to electron volts, and you should get a number. Well, that should look familiar to you from chemistry, but maybe not. You should get a number of, I think, 13.6 eV. So see if you can get that. Yeah, and that's what you're going to post in the discussion. So again, you're doing a derivation using those equations to get this equation that's highlighted in yellow here. So you're using the first 4 equations here to get this. And then you're going to use the equations that are highlighted here in order to get, let's make that the same color, in order to get this. And see if you can plug in the values here. Remember, h bar is equal to Planck's constant over 2 pi. It's very commonly used in quantum mechanics. Coulomb's constant is 9 times 10 to the 9. Newtons meters squared over Coulomb squared. Mass of an electron, you should be able to look that up. Charge of an electron, well, mass of an electron is 9.11 times 10 to the negative 31 kilograms. H bar we got already. That's a 2, not a Z. That's a 2. And then charge of an electron is 1.6 times 10. Charge of an electron or a proton is 1.6 times 10 to the negative 19 coulombs. So yes, see if you can plug those in and get those values. You should get 13.6 eV. There's a negative in front of there. Why is there a negative? Why do you think it's negative? Why do you think that this the energy of an electron that's in an orbit is negative? That's something you might see in AP Physics C, so think about that. Why is that negative? All right. So go ahead, try that, figure it out, and see you guys in cyberspace. Bye.